My name is Yalong, and my hands-on exercise will be computer vision classification for cattle food grading. And we will have a hands-on exercise on Google Colab that will be using Google Colab platform, so you will need a Google account. And we budgeted almost 2 hours, 1 hour and 50 minutes to actually work on this. So first, I encourage you to take a picture of this link and also send yourself the barcode and then go to the GitHub link now, because I will briefly introduce you what we are trying to grade in terms of animal food and the rough setup. So, do you need more time with the BR code? Okay. It's in the same GitHub repository that is with all other presenters. So, if you go to this link, you can open it now. What you will see is the description of this workshop, and you will see multiple files. We have the PowerPoint that is the same as what I'm showing you, and we have one image. This image, you can open that, so that you will see this is the how we collected the data. I work with Dr. Louis Tedeschi, Dr. Karun, as well as Igloo, who helped us to collect the video. I'm the computer vision guy, so after we collect all this data, we decided to crop, only look at the feed bank, and we want to know, using machine learning and computer vision techniques, when it is full, when it is empty. So we defined multiple fullness scores, 6 different scores to describe when it's full, when it's empty. And then we want to automate this process, because in that way you can set up a computer vision system yourself. This is a very versatile system, so you can apply this to many, many different problems you have. And if you go down here, the last file ends with IPYMB. This is the main file we are going to use. And if you click on that, it will bring you to a page that will have a button on top, a yellow button on top. This yellow button, if it shows up, you click on that yellow button, it says Colab, and it will take you to the actual Colab. Just 1 second. Did you open the page? Oh, you did? Oh, some did. I think it's something on my computer. So previously I opened this already. Huh? Okay. Sorry. Okay, please take a picture. I think what is happening is that the traffic is suddenly too high. Perhaps GitHub needs some time to respond. Keep refreshing that, and I can move on with the presentation. I opened this earlier before, so I do have one copy on my end. I can show you. After you click on the yellow button, you will have the Google Colab. And on the left hand, you will have this folder icon. And you can run all the code you have. It will download all the feed grading pictures from my Google Drive onto your Google Colab. I think Hector and Ming, they are helping you if you need help. You can download it and work on your own computer as well. Yeah. Any success? Like no one can open it? Okay. I opened this 20 minutes ago, so we made sure this was working. Let's give GitHub a little time. I will move on with the presentation. Okay, with the presentation, I budgeted, roughly speaking, 2 hours. I will go over the fundamentals of machine learning, which is the fundamentals of AI. I will use a very simple example, and this example is consistent over this whole presentation. And I will talk about training and the testing, as well as how we understand the results. This is highly technical, but highly understandable. I'm sure everyone can follow this. The reason is this. A lot of times we use AI and use machine learning just as a term to say the model learns. But how actually it learns is very important to understand this system, especially when you are designing some. And after that, we have the GitHub set up for 2 experiments with the data prepared. Hopefully we can get to the Google Colab. If you have questions or you have some success, raise your hand, let me know, so we know what's going on. The first experiment will be the simplest neural network, banana neural network, that will classify the input images into different grades. It will not work very good. It works better than guessing work, but not so great. And the second part, we will improve this using the stuff we talk about in this workshop. So I will start with the simplest example. We have x and y. X is equal to 1 to 5, y is 10, 20, 30. For this audience, I don't have to tell you, normally people do linear regression. Y is equal to ax plus b. Nowadays, for AI, machine learning, neural network, all those terms refer to this type of structure, which we have one, y, and many. People call this neuron, so we have the H1 and H2. People call this neuron, saying this is mimicking brain, but I think it's just number holders. So a typical network will have a lot of number holders, but here we only look at 2. And then those 2 will give you the y by the following. So we will go slow in the beginning because I want everyone to be able to follow. So x1, I give it a number because later we will scale up. We will have many x input, but now we have x1, and x1 will be multiplied with w11 to give h1. Similarly, x1 times w12 is equal to h2. So this is fairly simple. And then we time that with another set of w's, w21 times h1 plus w22 times h2. If I add them up, it will give you the y output here. So this is fairly simple, and why it's called W? You heard about weights. It is because this is called weighted sum. That's why we chose W to represent. So each line in the connection here is one weight. And we will mainly study how we adjust those weights. This is where I lose people, because the audience you have is correlated to how much math you show people. But this is fairly understandable. So the first line is copy-paste. Second line is that, let's say we randomly initialize all those W's, give it arbitrary numbers, and we can make one prediction, which is called Y-pre. This will be wrong, of course. And we want to measure how far off it is from the truth. So we have Y true. And where is Y true? Y true is in the table. So now, if we only look at the first row, the green X and Y pair. So X is equal to 1, Y is equal to 10. Now we take a closer look for the loss. You can plug in X. And also, at the same time, I want to do one thing. I want to fix W1, 1, W2, 2, as well as W2, 1. I want to fix them to equal to 1. The reason is that this is simpler to calculate. And I want to only look at W2, 2. I want to study how I change this 1W with respect to loss. So you can organize this, and you have this parabola function. This is high school mathematics. The idea is that I want to only look 1 for now. So if you have this loss, you can write it out. You can plot it. You can plot it so that we know when W22 changes, how the loss will change. We know this is a parabola function like this, and it's symmetrical. And I have a little more mathematics at the bottom. This is the slope, 2, 2. What I mean is this. When we can start with a random W22, we can guess. W22 is an arbitrary number. When the W22 is on the left side, the slope is negative. And if the W22 starts on the right-hand side, the slope is positive. Okay, so this is the core of machine learning. I will come back to this slide. So the core of machine learning, if you learn anything in this workshop, is that we start with the random W's, W22, and we call that old W22. And we minus that with the slope times a very small learning rate. This is a positive, very small number, 0.0001. Now, if W is on the right side, it's positive. I minus a positive number, so I'm moving this W a little bit to the left. On the other hand, if the W22 is on the left hand, we minus a negative number. We move the W to the right hand. Both ways, it will move towards, move the W so that we have a smaller and a smaller loss here. So this is the core of machine learning. It's always doing this. And we are using this slope extensively. And this slope has a fancier mathematical name. It's in red, but it's the same. In red, this means we call this partial derivatives. Partial derivatives. It means how much loss will change if I change W22 a little bit. So slope 22 is covered, and we know how to find the best W22 to find the best loss. And now I'm going to scale up. Now let's look at one more W, W11 here. So in 2D space, the curve was a parabola. And now we make it 3D. We look at W11 and W22 all together. So it's a surface now. But it's the same. The old W11 minus slope 11 times the learning rate will give you the new W11, and so on and so forth. So in my class, normally this is where I have a quiz asking, did you really get this? If you get this, we can scale up even more. So we have 4 connections in this network. It's very simple. We have 4 connections, 4 lines. But if we look at all the W's, all the 4 W's, we cannot visualize this anymore. The most you can visualize is 3D. Some smart people can do 4D, but that's about it. So now I replace the slope with the correct notation, which is what you might have seen in different papers, and a lot of YouTubers, they show this as well. So this is essentially slope with respect to each W. Everything else is the same. And it is a lot to write, so no one wants to write this much. So you might have seen this. This is also a very good quiz material. You group all of them, all the W's, new W's, into one vector. So, and then all the old W's group into another one. And now, a special one is all the slopes, all the partial derivatives, we group that into an upside-down triangle. This upside-down triangle has a name called the gradient. It always has the same dimension as the W's in front. And the learning rate is always very small. So we have the complete understanding of a neural network now. This neural network is very simple, but we know exactly what's happening. And this process will happen millions of times until we have a good loss. So this is, if you take anything from today's workshop, perhaps this equation should be a good takeaway. And now, I think we are ready to scale up. If we scale up, we have multiple input and multiple output. It works the same way, but we have way more W's now. So I often say that I don't really need computers. If I have 500 students, they're all very good at computing the gradient. They can all do this and update. A update to B, to C, and so on and so forth. I don't need computers. I can do this by human power. But computers are better. So oftentimes I ask people, how many connections are there in between the first and the second layers of placeholder? How many W's? How many lines connecting all 3 and all 5? Three times 5? 3 times 5. Yes, 3 times 5. So this is a good exercise when you count this, because later in Python, this is in the code and you don't know, and PyTorch and Google and Facebook, they don't tell you how many are there. It's a good exercise also when you develop machine learning stuff yourself, because many times you don't match. If you don't match them, it's not going to work. It's going to give you a dimension mismatch error. Speaking from experience, I learned this hard way. So the second layer will have how many connections? It's like a standoff. Either we'll have 25 and so on and so forth. So it's important when we build networks, we know how many connections we are building. And then we have W as weight. Traditionally, people add bias. After you sum up, for example, H1 is equal to X1 times W11 here, plus X2 times W12, and so on and so forth. After you sum everything up, traditionally people add a bias, but this is not necessary. Without it, it works. Okay? Now we are just one more step away from completely having a working functional neural network, which is activation function. It's very easy to understand. It's just that the name is very confusing, like activation function. What do you mean? If you sum up the if you sum up the H1, H2, and so on and so forth, activation function says this. If it is negative, make it 0. If it is positive, keep it positive. The reason is this. The reason is that without activation function, what we are building is linear. We have linear x times a big parameter, and then give us y. But a lot of problems we study is not linear. So we want to make this activation function at each connection. So to add nonlinearity. So it works for image recognition, it works for TikTok, Netflix recommendation, it works for large language processing. So activation function, you cannot get rid of it. You have to have activation function. But the form of activation function, it depends on you. A popular one is ReLU, which means if we have 5 as input, 5 output. If it is -5, the output is 0. So this is one way. This is the most popular because it's cheap. There's no extra computation to do. You just make it 0 if it's negative. There are many different activation functions, sigmoid. The idea is to make it not linear. So now I'm going to talk about a little bit about the output types. So working with the precision livestock farming, a lot of work is how we arrange the input and output. This output can be a regression problem, a classification problem. We can extract some features, and we can combine all of them. So regression, body condition, weight prediction, etc. Classification is what we are going to do today to classify if the bank is full or empty. So a lot of effort goes into how we structure this neural network. This network is highly flexible. It can work with any numerical data input and any numeric data output. So, for example, X is how much I eat. X2 is how fast I run. I can predict a person's weight and height based on those input. This is one simple example. Let's say we collect a lot of people's data, and then we can make random predictions, 110 pounds, but the ground truth is 150 pounds. Then we measure the error, the loss. Previously we had 1 square loss, but there are other loss. But the idea is that we measure the difference between the prediction and the truth, and we update the lines, and then we do it little by little until we reach the best performing loss. So I think for this audience, I don't have to go through this mean average error and mean absolute error, mean square error can be losses. You can also design your own loss as long as they are differentiable. As long as they can provide you the gradient, you can do the update, it works. Okay, one special output type is classification. Previously we said that we have 2 outputs, for example Y1 and Y2, representing chicken and banana. So we have an image input. We want to tell if this is a chicken image or a banana image. We want to prepare the output in one specific way. So this specific way is called one-hot encoding to prepare the truth, not the prediction, the truth. So for the label for a chicken image, it's 1, 0. The first is corresponding to chicken. The second it corresponds to banana. This is flexible. You can increase this to 5 different classes: chicken, banana, dog, cow, etc. And if it is a banana, we only give the 1 to the corresponding class. Everything else is 0. So this is the way we encode the truth. After we encode that, we want to process the prediction, y predict. So we saw previously that the prediction of all y's, for regression problem it works, but for this problem we want to normalize all the y's so that they sum up to 100%. Because it is a classification problem, it can only be either chicken or banana. It cannot be both chicken, banana, and dog, and so on. So we have a mathematical way to do this. You don't have to understand this. This is not the important part. The important part is that whatever y we have 5 y's, for example, here. We normalize it so they sum up to 1. So we can pick the highest probability as the prediction. So in this case, it's chicken, banana, and banana is the highest. So we predict the image is a banana, picture. This is only for classification problem. And later we will combine classification problems with the regression and et cetera, et cetera. So like I discussed earlier, the input image will be classified, will be processed by the network to guess how likely it is to be a chicken, how likely it is to be a banana, and compare to the one-hot encoding ground truth we prepared earlier. So now the problem is how you measure the difference between them. Now a lot of people will run away again because this is too much math. The reason, I don't know why people always start with the binary cross entropy, but it is in fact very simple. So the method we use to measure the predicted chicken banana classification against the truth is to use a function called cross entropy. And this is too fancy. Why? What do you mean cross entropy? Doesn't make sense. So if you look down all the way, it is actually a log, and you take the percentage. It's a negative log. Take the predicted probability. And you sum it up. So y true is either 0 or 1. You really don't have to care too much about it because we're only considering the positive case. Because y true, when it is 0, we don't really work with it. So I will come back to this. Now, if we look at negative log, it is fairly straightforward. We only consider 0 to 100% prediction. Negative log looks like this. It is also simple to understand. When the model predicts chicken with high probability, for example, 80%, the loss is small. So we make very small changes. Remember how we get the gradient? When the model is very not confident, 20%, this is the chicken. We make large changes in the weights. So now we go back. This is essentially how we calculate the cross entropy for classification problem. And this is a standard. GPT uses it, self-driving cars uses it, because for classification we use cross entropy. And there is an advanced version which is called binary cross entropy, which is not that difficult. It's just that we consider the negative cases. So altogether, we know how to do classification. This is the case for binary classification. So previously, we looked at negative log likelihood going down, which is this red line, when the label is true. Now we just mirror this. So when the truth is 0, it's a negative case. The model gives a high probability that it's not this case. Then we make higher change. So we consider negative cases in binary classification. So if you have a problem and you want to get started, do a binary classification because it considers positive and negative cases, and you will likely to get a better result. And start from there, you can include more classes. Okay, so up until now, I'm talking about all the foundational knowledge about neural network, machine learning, and etc. I want to deliver two concepts. One is weight update, which is this one. A lot of people call this learn. A lot of people call this fit. The learning, and in mathematics, people call this back propagation. Geoffrey Hinton invented this and won Nobel Prize last year. It's all the same process, which we just studied. It's compare the prediction with the truth and update all the lines. So it's backwards. And you see this formula again. This will be quizzed many times in my class, but this is, if you take anything away from this workshop, this is how we update the weight. So this is the backward pass. Another use case, another process is forward pass. Some people call this inference, some people call this testing, validating, deployment. It's the same. So we use those W's, we calculate it, and then there is no truth to compare with. So this is the most important difference between use the model and update the model weight. So those are two processes. And this is the last slide about the technical part and the foundational part, fundamental part. And this is the fun slide I have. So for a binary classification case, you predict you're pregnant, and you are in fact pregnant. So it is a true positive case. And if you predict positive, but in fact you are not pregnant, so this is a false positive case. And so on and so forth. So we have the table. We call this confusion table, confusion matrix. So out of 100 patients, you have an AI, for example, diagnosing pregnancy. And then you can measure. You need the truth labels for this. You can measure how successful is this AI using this matrix. For example, precision. We count how many true positives divided by how many total predictions you make. And then you have the percentage. And you have recall, F1, accuracy, and so on and so forth. This is the standard. Most people report this. And if we use all the data we have in the table, the 3x2 table, we use all the data and update all the W's for one time. It's called one epoch. So I mentioned that we do 1 million epochs. So over the epochs, the loss will steadily go down. The worst will happen is that the loss will plateau, will become flat. If you see a loss that is going up when you are training, something is wrong. And a normal practice is that we divide all the data we collect into training and testing. We build the model on training, and we test on testing, of course. A normal ratio is 80 to 20%. Testing, I use testing interchangeably with validation because they are the same. They apply the model you trained on unseen data. In some cases, you have enough data, so you do validation when you are training, and you test on a separate set. In some limited cases, you can use validation and testing. The idea is to generalize the model you are building. Okay? And then there is a line in between. When you are training many epochs, at some point, the performance on validation or testing will not be as great as training because our model is specializing on training. The loss is so low, but the loss on testing will go up. So on the right hand of this line, it's overfitting. We want to avoid that. On the left hand, it's underfitting. We still have some room to improve the model. It is up to animal scientists to make sense of when to stop and when to save the best performing neural network. Okay, we are ready to move on to the experiments. We reviewed how neural network works. Can you show me your hand if you can open the GitHub page? Good, it worked. Okay, I can move on, and then we will work until to the simple neural network section. I will show you later. So computer vision, to build cameras, it is fairly simple. You just buy a magnifier and put the tracing paper on the back. You have a camera. This is my backyard. It's the same way as how our eyes work. All the light emitted by sun, by the light bulbs, reflect on objects, reflect all the lights they don't absorb into our eyes. So in the case of cameras, the light will pass through a hole. This is called the pinhole principle. It was discovered a long time ago in Persia, I believe. And then the light will get reconstructed on the back in a very in the correct focal length. You can reconstruct a very clear image. So this is how cameras work still. But now, instead of using a tracing paper, we have light-sensitive sensors, electrons. The idea is that we apply steady voltage on both ends. And when the light shines on those sensors, the voltage will change. We measure the voltage change, and then we have the digital image. So the filters, you can see we have 3 colors: red, green, and blue. This is developed by human because we see red, green, and blue lights the best, and in combination of them, you can see an actual dog on your screen. You are not seeing the true color. Your eyes are deceiving you to trick you to think you are looking at a purple flower, but it's a combination of RGB colors. Now, all the images we take, I want to emphasize that they're all tables of numbers. So this is a grayscale Abraham Lincoln. How we make the image is that we have all the pixels. This is a very small pixel space. And when there is no brightness, when there's low light, the color is black. The value is close to 0. When the color is very bright, the highest color we have is 255. This is related to how people used to build chips. They used to build binary chips, of course. It was 8-digit. 2 to the power of 8 is 256. And some very smart person decided to count, starting with 0. So we are with 255. That's the highest, brightest color. Now, you take an image. You have this table, or we call this a matrix. You send this matrix to your friends. You are sending those numbers. Your friends take those numbers and reconstruct the Abraham Lincoln on their phones. So that's how you see the Abraham Lincoln. So when we talk about computer vision, we are dealing with all the matrices here constructed by our camera. Now the rest is very easy. We are over the hard part. So this is one image, for example. We have numbers x1 all the way to xn. We move x1 here. We plug x1 here, x2 here, x3, and so on and so forth. We line all the pixel values up. And then we build a network fully connected. And then we try to classify. In our experiment, it will be 6 different classes. Now I can show you a little bit of the code. Oh, by the way, when we are doing the lab session, you can use the bathroom, so I didn't budget any break. Feel free to go and come back. Yes?
In that previous slide where you had the layers,
This one? Okay.
so there you just have a vector of x values. There's no positional information there?
That's a very good question. For images, we need positional information. But for now, I'm showing the banana simple neural network as an example. Yeah, by the way, any other questions about how it works? Because I think that's more important than actually coding it up. I'm happy to discuss with you. And normally I will pause for a long time until someone asks something. Okay, but we don't have to do that. Okay. So if you just opened this page, go to the GitHub, and then find this last file that ends with IPYNB. This is the Google Colab portal, which we will use. And here, you can read all the descriptions I have as well as the visualization. This is the empty bank. And in our experiment, we want to use this as grayscale, just so it computes faster. At the top of this file, go to open in Colab. So this is where actually you can use Python code to work with the images and stuff. So on the left hand, you have the table of content. For now, we are going to work until we reach the end of simple neural network. So this is going to implement what we discussed, essentially. And if you run this at the third cell or something, this cell is downloading a folder called mixture from my Google Drive. So do this now, and maybe GitHub will take some time to allow everyone to download this. But after you download everything, you go to this icon. You will find a mixture folder. This mixture folder will have 5 different classes organized. And if you click on some random example, you will see this is class S20. And then, for example, empty case will be this looking. We prepared this manually. Human graded this, and we are trying to build an AI to do this automatically over a long time. Okay. So, I don't know why I have the echo. Okay, now work on this, and before I let you go, I want to briefly go over what is happening. So we are importing a lot of libraries, downloading videos, downloading the dataset, which is called mixture, and we are making this image 128 by 128. Because we are building the same, we are building the neural network with a fixed size, the input has to be the same. You cannot just change a bigger picture and fit it into this. And we are also making this image a grayscale. And now we move on. We have 6 classes. We in total have 183 images. I chose this number because it's fast. And this is how it looks for S10, for example. And now we have splitting them for training and testing, loading them, visualizing them. Now this is the important part I want to spend like 2 or 3 minutes on. So the input, we line all the pixels up, 128 by 128 is this number. Linear this does not mean linear regression. This means fully connected. So I just give it an arbitrary number, 1,000. And I made 3 layers. That's all we need. And this is the syntax. This is the coding syntax. You don't have to worry too much about it. The output is where we should pay attention. The output is 6 because we have 6 classes. If you have only chicken and a banana, the output should be 2. So if you are building this for yourself, you change this to 2 for your cat and dog classification. And we see a lot of familiar words here. For example, ReLU. This is the default activation function. We see cross-entropy loss. They don't tell you what is in this exactly, but we know. We have SGD. So earlier I said this, the training method was called gradient descent. SGD means stochastic gradient descent. It means that if you have too much data, we divide them and do gradient descent one batch at a time. So you see a lot of familiar terminologies here, and you should understand this is learning rate, and so on and so forth. So a lot of changeable parameters here. You can also see the actual training in action. So what I like about Google Colab is that it will show you when it's training and when it is testing. If you track this, there will be a small green arrow here, and you can see when the model is trained and when it's doing evaluation, and etc. So if we look at the performance, it's not so great. It will be around 30% for classification. This is on purpose. This is better than guessing. If I'm guessing 6 classes, it will be 16%. This is then better than guessing, but it doesn't work very well. So I will give you 10 minutes to work, download, and play with the models we have here. And later we can talk about how we build stuff, especially for images, computer vision. You can raise your hand if you have questions. We can help you with the code. Yes? Which parameters you want to change? To improve the... you can, normally what I will do first is to change different learning rate, and of course increase the data size. I will do data augmentation, augmenting images as well as whatever data you can collect. And I will try to change the optimizer, but you have to know what you are looking at. Adam is slightly better than SGD, but all I'm talking about is a slight increase in performance. The best way is to increase the quality of your dataset as well as the size. Okay. I just realized that my time is the Texas time. It's 12. I was like, it should be 1. Why it's 12? So it's 1:30 now. We aim to end at 1:50. I believe that's the schedule. Now, I think everyone finished this, looked at the sample pictures. Now going back to, yes? Yeah, it was my bad. We end at 2:20. We have 50 minutes or so in this workshop. And now it is 1:30. So do you guys need more time or more questions you want to discuss before I move on? Yes.
And so can you speak to what I've done in the past and kind of try to optimize the number of books? Can you just let any light on why you chose 50 or considerations around that?
Yeah, the 50 number for epochs is random. I just choose 50. What you normally do is that you will monitor the validation loss as well as the validation accuracy when you are training each epoch. And when you are seeing, for example, 30%, all the way 30% after 10 epochs, that means the model has reached its potential. If it's plateauing, there's no need to train it more. So that's what I would do. I would monitor the validation. It's not training. You monitor the validation, performance, and when it plateaus, I think it's a good time to stop.
Is there like an automated post script to like filter that for you if you just wanted to run arbitrary numbers?
You want to run a large number, and I think there is a function called early stopping. Early stopping, and you just set after 10 epochs, if there's no improvement, it will stop automatically. Yeah. If there is no more question, I can move on. So we talked about the weights, and it did not work very well when we used the banana simple neural network. We just lined up all the pixels. Well, there is one type of neural network that is highly efficient to image alike data. It's called convolutional computation, convolutional neural network. How it works is it's all in this one slide example. It's very simple to follow. So let's say we have a kernel or a 3x3, just a matrix. Any number is okay. We apply element-wise multiplication, and we place this kernel. Sometimes people call this filter. We apply this filter or kernel at each position. So position 1, position 2, and position 3. What you do is that you multiply the kernel number with the position number and sum them up. So sum them up will give you 21, 19, 15, etc., etc. So everything will be, not everything, the image will be shrunk by 2 pixels, one on each end. And normally what people do is to try to keep the same size, so we have zeros padding around it. But you can imagine when it's a big picture, it doesn't really matter. It shrinks a little bit. This computation will preserve the spatial information, like the question we got earlier in the first part. you don't have to worry about how many kernels and what kind of kernels you apply, because there is a fleet of computer scientists working on this, racing on who can design the best kernel, who can design the best structure. So some people are working on this. You just use the best. The one we will use later in the example is called ResNet. It's one of the best performing in image classification. So roughly speaking, what they are designing is, for example, if you have the input 3 channels, RGB, your kernel has to match the input. So element-wise, so that element-wise multiplication can happen. So multiply by this, green multiplied by green, red, and so on and so forth, and you sum all of them up to Y1. Sum all of them up to one number. And then you have another separate set of kernels that all will go to the purple layer, and so on and so forth. So people have 50 different kernels, after 100 kernels, and they are connected in some innovative way, so that the whole convolutional neural network will classify the image pretty accurately. The input is this size by 3 channel, so we have the kernel that has 3 by 3 by 3 channel. And if we apply 50 filters here, the next kernel will have to have 50 channels to match. So dimension matching is very important in computer vision when you design this. And then eventually what we do is the fully connected, all the weights we discussed earlier. And then the output can be any number. I'm giving just 1,000 Ys as an example, because there are many established large data sets, not necessarily animal science, but daily objects, flowers, elephants, and helicopters, battleships. So one famous one is called ImageNet. It has 1,000 different classes, and this is what people used to train this on. There's another one called the Common Object Dataset, COCO. This has 80 different classes. I listed one more. It's called Common Crawl. This is all the text information on the internet, Wikipedia, Reddit, etc. So people, some computer scientists build data sets for a living. I think animal science, like in terms of what we are working with precision livestock farming, also needs some standardized data set. I went to USPIF, and a lot of students are working on this. They know how to use this, but all in-house. They're all using in-house data sets. There's no published big data sets like this. Later, we will look at how we leverage existing computer scientists' work by using transfer learning. Again, it's a big name, but it's very easy to understand. Transfer learning means that we just download well-designed model structure, and download the trained weights on PyTorch or TensorFlow. And then we cut the last layer, the last Y, replace that with our Ys. We have 6 Ys. They have 80 Ys. So replace that, and you are ready to go to classify all the images into your defined classes. I do have some extra transformer large language content, but that's for the next speaker. I believe that that speaker will speak about large language models. So let's go back to the code. So up until this point, we did a very simple neural network. It works better than guessing work, but not so great. Now we want to use pre-trained weights. So how we use that is it's very simple. Coding-wise, it's very simple, but a lot of people worked a long time to design a good structure. For example, this is called ResNet. 18 here means 18 different layers. This is the smallest. I want to use the smallest to save some time for us. And it is pre-trained. It's pre-trained on ImageNet, means that we are talking to PyTorch, send me this structure as well as all the lines, all the weights, so I can load them up and I can just use it. Now, the code here, this is adding one last layer of Ys. We want 6 Ys. So the length of class names, this is 6. We're adding whatever is the previous last layer on top of, we're adding this 6 Ys on top of whatever is the last layer previously. And again, cross entropy, atom. And one more thing is that because this ResNet was specialized in RGB images, we want to modify it a little bit to take our grayscale. Remember that we forced everything to be grayscale just to save some time. So we are converting everything into grayscale. That's all the modification we need. And then we train it again. Training is the same process. And you can tell in the beginning, we still have low performance, but the model is training. Validation accuracy goes up to 67% or so. This is some improvement from the previous simple neural network that shows you can download and you don't have to design everything yourself. And at this point, if you increase or change the learning rate, you can play with it. You should be able to achieve 80% or so classification in this small data set. And you can save this, save the weight, and you send your coworker this weight so that person can deploy this. Now, if you go down, we have the evaluation. This is the inference or deploy the model. We can see the ground truth is S30. The prediction is S30 with a 0.03 confidence. Another example, S10 to S10. With a confidence of 0.98. So this is how you visualize it, how actually you interpret the code. I will show you. But the second section, the next section is that we also collected a set of random grade feeding pictures. I believe this is 4,000 or so. It's from the same bank, but at a different time. We want to test if the model works. And run this code, you will have another folder here. You should be able to find it here. Random pictures for verification. And remember the funny slide earlier, the funny confusion matrix? So this time we don't have a binary, but we have 6 classes. So this is again the confusion matrix, but we can look at, for example, for all S10, 1,168 was successfully classified as S10 by prediction. But 129 was classified as S05. This is confused by the appearance as well as our data quality, I believe. So all together, you are supposed to look at 80% or so accuracy on this random test. Lastly, I want to rehearse what we talked about today. This is how you interpret or how you use one testing image. So for example, we are just taking the first image for all the input for test. And the ground truth label is 0 for this image. We get this by just using which folder it comes from. We know this is 0. Now, we make predictions. This is the raw prediction we have. 8.0, negative 1.8, and so on and so forth. So this is not understandable. What we do is that we use softmax to normalize it into probabilities that sum up to 1. And the first class has, each number represents each class. So you always have 6 Y predictions, and you want to pick the highest. So the highest after normalizing them is 0.99 for class 1. Everything else is close to 0. So if you visualize that for each class, we always make Y predictions for probability on that. And the first class has the highest. Therefore, we pick class 1 as the prediction. Now, in some applications, you might have 2 classes. They are not mutually exclusive. You can also design them so that they add up to the number you want and normalize them so you can have 2 predictions. A chicken and a cartoonized chicken, for example. They can be classified together. Altogether, this is the workshop that I prepared, and I think you can spend some time inspect the verification dataset as well as playing with the code here, try different images, and so on. So if you have questions, raise your hand. I think I'm ready to answer your questions.
Folks are open for questions.
Can you spend a little bit time on the question which Bob asked of how the does the order matter in the image pixels?
This one? Okay. So your question is?
So does the order matter in the image?
Yeah, it matters. So that's why the first section of the experiment did not really work, 30%. And then we used this convolutional process so that we can preserve the spatial information. So it works better. Yeah, I hope that answers your question.
Yalong, I have a question for you. So we use classes, right? So 0 to 5, or you have 6 classes, right?
Yes.
What do I have to do instead of, and I think the objective was really to identify if the feed bank was empty or full, right? So we had 0 to 5, 1 to 6. How can I change the model to, rather than telling me which class it is, what is the proportion, how the percent full that it is? Can I do that instead of having classes? So I have a picture and then it tells me it's 35% full or 35% empty, rather than having classes.
That will be a different arrangements. So we did a classification, so we have 6 different probabilities for each class. If you want a continuous value, perhaps that's a regression problem. And then if we can collect 5 kilograms, 5.5 continuous data for the weight, corresponds that to appearance, we can build some model to estimate the regression in terms of how heavy those bunks are. And then on top of that, if you want to do percentage, we can do percentage as well. But it's always easier to start with the classification because the entropy loss is easier to control because it's normalized. regression can be very big, and it's less likely to get started. But I think with some work, it will work.
I think some of the people here are really thinking about if we can use this computer vision to say how much is left, the amount that is left. Do you think we still can get that? But you said we have about a 30%, 33% accuracy for each class, right? So when we're training, the database was only 30%, 36%, something like that?
If we use the simple example, yes, it's 30%. If we use the pre-trained, it should be 70, 80%. And remember, this is for the demonstration purpose. I reduced the data set to 180 images. So you can increase that and improve the performance.
Good. More questions? Other questions? Questions in the back?
Huh? Transformer? Yes, I can, but I hope the next speaker won't be mad. Okay, so about the transformer, I'm sure the next speaker will talk about this, but I do want to share two links that I really like that perhaps the next speaker knows or he doesn't. The first link is called TikTok Tokenizer. You can go to this link from the PowerPoint I shared on GitHub. This is a cool website, shows you how GPT breaks down your prompt, the text. You can select all the current good models, and we are selecting GPT 4.0. Now, if I say I want pizza, it's color-coded. It's breaking down my words into I, and want, and pizza, and it handles typo, like this. So you break down, the GPT will break down the input, and then it will show you the index. The index of a lookup table. So when you say I want pizza-ish, FGGG, it's broken down into those smaller pieces. We call it a token. Roughly speaking, a token is a word. And you look up in a lookup table. The lookup table will look like this. So I want pizza will have a list of numbers to represent I, represent want, represent pizza. So this is a cool visualization tool to show how we embed different words. And the way GPT works, or tokenization works, is that you want to vectorize, you want to assign numbers to I want pizza. So if you plot them in a 3D place, I want pizza are closer than spore in some biology literature, than in some food literature, in which case I want pizza are very close. They appear almost always together. So Google did a very good job of visualizing this relationship. So this is the second link I want to share. So Google, they have their own. First you break the words into smaller tokens, and second you turn the tokens into numbers. So Google did a good job of visualizing how you break, how you encode those tokens. This is showing only 3 dimensions. We have more dimensions, but we cannot show that. So for example, anatomy. Randomly I clicked on this. The closest, this is the distance. The closest is psychology, biology, and so on and so forth. The further one is animal, genetic. if you try another word, faculty is undergrad, grad, very close. Institution is slightly less frequently appear with the faculty. So this is how current methods turn tokens into numbers. Now, again, this is an open field. All companies, they use different ways. OpenAI has their own closed-sourced vectorization tool. They also break down words separately, and they don't tell you. What we have now is the open-sourced version. So, and it all changed meanings because you build a huge network. The network is called a transformer, and you predict the next word. I want pizza from Pizza Hut, Pizza Hut from 15th Street. So each time I predict the next word and so on and so forth. So this is the two links I want to share. And I'm happy to take other comments and questions. Yes?
Yeah, so I don't know if Karun asked this, but can you go back to the slide where it showed the 3x3 scanning? And yeah, that one. So it might be just your visual. Oh, you had it.
I see.
It was, yeah, down to slide 41. So maybe it's just the visual, but I see they overlap.
Yeah, they do overlap.
Okay, does that matter, or if it's getting that grid and it's overlapping, or?
They are overlapping on purpose because I'm applying the kernel. I'm applying the kernel at the blue and then green. So there is a little overlap. And you can set it up so that it moves 2 pixels at a time and 3 pixels at a time if you want to speed up the computation. But most people do slide one by one.
Yeah, thank you.
Yalong, any more questions, folks? Yalong, that's a good question. I want to ask you this because what I was paying attention whenever we were simplifying this, the edges, whatever number is at the edges of this, it only gets used once.
Yes.
Whereas all of the other numbers, they are used more than once, because if you go back to your the two more, yes, the next one, the next slide. You see, when you look at your the animation, you're moving that little square, the 3x3 square. So it is averaging everything that is in the middle. It's getting averaged like 1, 2, 3, 4 times. It depends how it is. But the edges, it uses only once. So the value that is on the edge is only used once. Do we need to add a weight to that, to the edge, or not?
Yes, I think you are right. It's only used once. But so this is a 5x5 image as input. If we consider a 228 by 128 by 128 image, the pixel, the 1 pixel at the very edge is not that important. That's how I think.
But you see, it's being used only once. So when you start that column is just used once.
Yeah, that's
number.
true.
So the edge is not being. It's actually being penalized in a sense. I think it's overweighting what is in the middle. I think that's what is happening when we do this. I've seen some folks actually adding some weights to the edge number.
Like add weights
Yes.
around this?
Yes.
Yes.
So
Some people do that.
all the little squares have a weight 1, and everybody outside has a heavier weight Otherwise, you're scaling it down, you're weighting it towards the middle, towards the center of the picture, if that's a picture. That's what I have seen. Any more questions, folks? So that's a possibility of actually changing how we analyze these images. I think we're missing some of that, even though it's only the edge. It's only one pixel, right?
I would just comment what you're saying. For us, maybe in a pasture setting, a wheat pasture or a Bermuda grass pasture, that's probably more or less irrelevant because you're going to be so homogeneous. But in the range environments that we work in, if we were trying to use this to characterize a land surface, that could be hugely important depending on how heterogeneous that landscape is. So we would probably need some sort of a, and there are different landscape measurements of heterogeneity that we could apply to that, but that would probably be very important in that case.
Because if whatever we're trying, if we're trying to identify a, let's say on a pasture, for instance, if we're trying to identify when a pasture goes from good to bad, if that section is not in the middle of the picture, if it is towards the edges, it's going to have a much lower weight than if it is right in the middle of the picture, or whatever the image.
Water, soil type, slope.
Yes.
100 different things.
So I think we probably need to think about using different weights there. Any other questions, folks?